Hi everyone, I'm Santiago Vargas.
And I'm Rebecca Drucker, and today we'll be jointly presenting our work, BBR Buffer Bloat in Dash Video. We also collaborated with Aishwarya, Professor Aruna, and Professor Anshul. So why did we want to study video and BBR specifically? It's because video streaming is a popular and growing application that accounts for over 60% of internet traffic. And BBR is a new congestion control that has been widely adopted, especially by large video providers like YouTube, and it now accounts for some 40% of internet traffic. So with those things in mind, we investigate video QoE under BBR.
So before getting into our work on video and BBR, let's just do a brief background on congestion control and buffer bloat. Congestion control algorithms effectively decide on how fast to send packets. If they send packets too slow, they underutilize the network. But if they send them too fast, they can run into problems like buffer bloat, which is excessive queuing delay in large network buffers. Let's see an example of this. So on the left-hand side, we have a sender. On the right-hand side, we have a receiver. And in the middle, we have a bottleneck router. The sender sends packets to the receiver. And if it sends at an adequate rate, packets don't build up in the bottleneck router and there's no congestion. But if it sends too fast, the bottleneck router accumulates packets, causing high queuing delay, and you have the problem with buffer bloat. Now, BBR is a new congestion control that's designed to combat this problem with buffer bloat. It does so by estimating the bandwidth delay product, or BDP for short, and using the BDP to set its sending rate. Now, BDP is a theoretical network capacity, and it's computed as bandwidth times propagation delay. Let's look at an example of how this looks in terms of RTT and delivery rates. So we have the RTT graph on the top, we have the delivery rate graph on the bottom, and in the x-axis, we have the amount of packets in flight. Now, as the amount of packets in flight grows towards BDP, your RTT stays very low, but your delivery rate increases because you're sending more packets in the network. But once you hit BDP and you keep on increasing the amount of packets in flight, you actually get buffer buildup. And this is because you've already reached the theoretical network capacity, and any extra packets in flight are actually just sitting in router queues, causing extra queuing delay. Now, BBR estimates the bandwidth as the maximum delivery rate, and it estimates the propagation delay as the minimum RTT. So BBR's operating point is actually at BDP, where there's no extra buffer buildup. So in this way, BBR is able to avoid the problem of buffer bloat.
So now that we understand a little bit more about how BBR works and about buffer bloat, let's talk about the experiments that we did to measure video QoE under BBR. We have this private LAN setup where a server and a client communicate over a router. We also did our experiments in the WAN. And we set the congestion control on the server to 3 different congestion controls, BBR, BBR2, and cubic. And we also set our HTTP version to HTTP 1.1 and HTTP 2. On the router itself, we set the latency at a default value of 100 milliseconds, and we set the bandwidth at a default value of 25 megabits per second. We also are able to set the buffer size on the router, and we can configure this to some wide range of buffer sizes to really do a broad sweep. Then on the client, we check out 5 different ABR algorithms. An ABR algorithm is an adaptive bit rate. This is the algorithm that Dash players use to choose the quality of the next segment. So we also collect our QoE metrics on the client. The segment quality ranges from 0 to 10. We encoded a video in 11 different bit rates evenly spaced apart, with 0 being the lowest and 10 being the highest. And we also collect stall rate, which is a measure of rebuffering. If the stall rate is greater than 0, then the client experienced at least some rebuffering. In total, we performed over 700 experiments covering a wide range of network conditions and application settings. So the main parameter of interest for us was buffer size, because BBR is supposed to combat buffer bloat, and you would think that it would have higher video QoE than cubic, which is not configured to help with buffer bloat and would have poor performance in deep buffers. So surprisingly, we find that there is poor video QoE under deep buffers. I will show you a graph with buffer size on the x-axis and average segment quality for 3 different congestion controls on the y-axis. So for the first 3 buffer sizes, 10 kilobytes to 1 megabyte, small buffers, the performance is fairly good for all of the congestion controls. But after about 3 megabytes, the quality drops off steeply for all 3 congestion controls. Now we expect this for Cubic because it has no way of combating buffer bloat, but it's surprising for BBR because it specifically has been designed to work well in deep buffers. And 3 megabytes or 9 BDP in the context of our network settings is not a particularly large buffer. You could find a buffer this size in all kinds of networks. We confirmed this result across HTTP versions, RTTs, ABRs, and WAN settings, everything that we said in the previous slide, and this result holds.
So since we run a wide range of experiments and find that BBR still has poor QoE under large buffers across all of these experiments, this hints at a deeper BBR problem. So we dig in and we observe one thing. Our first observation is that this low QoE under deep buffers with BBR is due to high RTTs. Now, these high RTTs slow down video downloads, which effectively lowers the throughput and also causes things like more stalling because videos take longer to download, both hurting QoE. So we show a graph of RTT with log scale RTT on the y-axis and two different buffers, a shallow buffer, which is a 100 KB buffer, and a deep buffer, which is a 10 MB buffer. And we recall that there's a 100 millisecond propagation delay set in our network. Now the shallow buffer at the median only has 100 milliseconds RTT, which means that there's no extra queuing delay it sees. However, the deep buffer, its median RTT, is 750 milliseconds, which means it sees a whole lot more queuing delay, and it represents a 7 times increase compared to the shallow buffer RTT. Now, these high RTTs under deeper buffers reveal that BBR is experiencing some sort of buffer bloat. So why is there buffer bloat under BBR? And there's actually two reasons for this. The first one is that there's BBR bandwidth overestimation, and the second one is that BBR is stuck in its startup phase under these deeper buffers. Now, for the rest of the presentation, we'll go over the first point, which is the primary point, but for details on the second point, you can refer to our paper. So looking at BBR's bandwidth overestimation, we present a graph of BBR's bandwidth estimate on the y-axis, and again, our two different buffer sizes on the x-axis. So recall that our network capacity is, network bandwidth is set at 25 megabits per second, which is the dashed line. So under the shallow buffers, we see a median bandwidth estimate of 25 megabits per second. But under the deeper buffers, we see that BBR overestimates bandwidth at about 80 megabits per second, which is a 3x, or it's greater than a 3x increase from the shallow buffer. Now, recall that BBR's bandwidth estimate is important because it uses this bandwidth estimate to measure BDP and uses BDP to control its sending rate. So if BBR overestimates bandwidth, then it increases its sending rate to beyond the network capacity. And if it sends too much, then this is what causes BBR buffer bloat because router queues are filled.
So now that we've determined that BBR's bandwidth overestimation is the cause of buffer bloat, we can ask, what is causing BBR to overestimate bandwidth in the first place? To understand what's happening, we talk about bursty networks. A burst is a sudden temporary increase in the delivery rate above some baseline bandwidth. This can occur for a number of reasons, but in our experiments, it happens because the router has been configured to absorb bursts, and this is a fairly common setting. To illustrate the problem that bursts cause for BBR's bandwidth estimation, I will show a synthetic example that is similar to what we see in our experiments. So on the x-axis, we have time in RTTs, and on the y-axis, we have delivery rate in megabits per second. Here is a group of delivery rate samples. Well, you can see that most of them are at or below 25 megabits per second, our set network rate, but one of them is all the way up at 75 megabits per second. Recall from our background on BBR that BBR uses a 10 RTT window over which it takes the maximum bandwidth sample to choose its bandwidth estimate. So in this case, over the window shown, BBR would estimate the bandwidth at 75 megabits per second, even though the true network capacity is only 25 megabits per second. So you would have to wait until that one bursty sample exits the window for the bandwidth estimate to go back down to the actual network capacity of 25 megabits per second. So how does this actually affect the video application? We're going to show a cycle that exists between BBR and the ABR of the dash player that is driven by bandwidth overestimation and oversending. So keeping in mind that BBR is always sending too quickly because it's overestimating the bandwidth, the router queues are going to fill up and RTTs are going to increase. Then the ABR's throughput estimate will drop because it sees lower throughput due to these inflated RTTs, and it will choose lower quality video segments. These lower quality segments are smaller, and so sending less data allows the router queue to drain and the RTTs to go down. Now that the router queue has drained and the RTTs have dropped, the throughput estimate can go back up because what little data has been sent quickly, and the ABR will now choose higher quality segments again. But those segments are large and it's a lot of data to send. And now that you're sending way too much data way too quickly, the router queues fill up again and RTTs go back up. You can actually see this cycle in graphs taken of our video experiments. The top graph shows the RTTs over time, and the middle graph is the ABR's estimated throughput, and bottom graph is segment quality. The red regions on this graph correspond to the red areas on the cycle.
So now that we understand that BBR's bandwidth overestimation is caused by these network bursts, which hurts video QoE, let's talk about BBRS, which is a BBR with a modified bandwidth estimation technique that uses sampling. Now, the two steps to BBRS's sampling mechanism is treat bandwidth measurements as a history of samples. And the second one is to discard excessively high samples as outliers when estimating the available bandwidth. So referring to our previous synthetic example, we see that there's still a high spike in the delivery rate at 75 megabits per second. Now, traditionally, BBR would look at this and estimate the network capacity to be 75 megabits per second, which is an overestimation. But using this technique of discarding outliers, we would discard this high burst at 75 megabits per second, and BBR's new bandwidth estimate would be 25 megabits per second. Now, we do present this solution not as a generalized solution for all workloads, but just to validate our results that we see under deeper buffers. So we plug BBRS back into our experiments to see if it actually improves video QoE. And we repeat our experiments under deep buffers, and we show the results in the graph. So on the y-axis, we see segment quality, and on the x, we see different BBR versions with the blue bars showing vanilla BBR, and the lighter bars in yellow and orange showing BBR with our modified bandwidth estimation technique. And we see that we do expect a low QoE under deeper buffers under normal BBR, and we see QoE segment quality is about 4. But with our new bandwidth estimation technique, we see near ideal segment qualities of about 10, and we see similar results in stall rates with virtually no stall rates. And these results are very, very similar even to shallow buffers. So we conclude that BBRS accurately measures the bandwidth estimate and is able to improve video queue because of that. So overall, this study measures the performance of BBR and dash video under many different network settings. And we find that there is poor video QoE under BBR, which is specifically under large buffers, which is not expected since BBR was designed to combat buffer bloat. But BBR, in fact, does suffer buffer bloat, and this is due to bandwidth overestimation. So we present BBRS with a modified bandwidth estimation technique that improves video QoE even under deep buffers.
Thank you so much for listening to our talk. We're here to take your questions.